going to just finish our very, very brief foray into chaos here with one more example. And it's coming back to a pendulum. A pendulum is a very, very simple example, and the pendulum system has only two variables, position and velocity, and it's never going to exhibit chaos. But if we increase the dimensionality just a little bit, for example, by hanging a pendulum off a pendulum, then we get something which can display very chaotic behavior. And I hope this is going to illustrate it all over my text. That's fine. This is a double pendulum, and you can see the apparently chaotic motion, highly unpredictable. And once more, this is a system which, if it were started in even a tiny, slightly different initial state, the trajectory would rapidly become dissimilar to this trajectory. So pendula have their secrets too. And this is an interesting fact that if we speak of continuous dynamical systems where time is a continuous variable, then the system needs to have at least 3 dimensions to exhibit chaos. This system has 4 dimensions because each part of the system has a position and a velocity of its own. But with a 2-dimensional system, we don't get it. But in a discrete dynamical system, we just saw chaos in the behavior of the logistic map, so it can do it with a single variable. Right, time to move on. If death is the ultimate attractor, then life is a transient. Life is something which passes. So attractors, in some sense, represent the ultimate fate of a system. It's long-term behavior, where it's going to go, no matter what, no matter where it starts. But in very many systems, we're interested not in long-term behavior, but in what's going on right now, in the melee that is living. These are transients, and we mentioned before that when you pluck a guitar string, it oscillates, and that oscillation dampens, and it comes to equilibrium in a state of rest. That's a point attractor, but what we're interested in when we play the guitar is, of course, only the transients. Transients are very important because systems may take different paths to the same end goal. So here is a record of the error at the output node for each of the 4 patterns in the exclusive OR problem set. Training cycles are shown on the bottom, and as you can see, the error for all 4 patterns reaches a very low value. This is a training progress for a network that learns the 4. And the average error, shown there with the mean, also descends monotonically. But it's interesting to note that the error on the individual patterns follows a rather more colorful course. And in fact, for the pattern 1-1 in this specific instance, we can see that the error on that pattern climbs before it falls, exhibiting non-monotonicity. Now, you remember that non-monotonicity in learning is something that the developmental psychologists have been long very interested in, because such examples of non-monotonic learning, as in the loss of the ability to make distinctions that one can originally make, has often been taken as a sign of different stages in the cognitive activity of the developer, as if we were learning in a different manner at different stages. Here, in this very simple example, we can see non-monotonicity coming out of a single learning procedure on a single data set. It still may be the case that during the transient, as we approach a final equilibrium, the path is wobbly. Right. Dynamic systems opens the door to talking about another very, very important concept, and that is autonomy. In everyday language, autonomy means sort of being a law unto yourself. It comes from autonomos, a law, self-law in Greek, and we use this in various senses, many of them very important in our everyday conversations, and in particular in our political conversations. We speak of the autonomy of the body, for example, as something which is of ethical concern. Or we can speak of the autonomy of a region within a larger form of government. Or, to taking it away from the geographic context, we can speak of the autonomy of different parts of the system of governance. So the judicial, the executive, and the legislative usually each have their defined spheres of action and defined spheres of interaction, so that one can speak of autonomy within the sphere of action of one branch of government. Autonomy is very, very important. And as we approach the question of autonomy, what we're doing is we're asking who's responsible? What is the origin of activity by something? This takes us back to the distinction we had between dynamics and kinematics, both of which refer to change. Kinematics, however, merely records change, something that happened, whereas dynamics speaks of the causal chain that gives rise to change. So this underlying cause, if it lies within the system of itself, then we may speak of the autonomy of the system. But a system may change because it's kicked, for example, and in that case the change comes from outside. So these are heady philosophical questions, and they involve drawing on very many concepts to do with embodiment, law, all kinds of things. We meet the notion of autonomy in a very minimalist sense, carved down within the formal vocabulary of dynamic systems, and it's a very, very useful sense. It provides us with an analogue for thinking about autonomy in the real world. It doesn't tell us about the real world. Mathematics is a formal exercise, and all mathematics can provide are formal models that may or may not correspond in some sense to the goings-on of the rich and confused world. We draw a basic distinction. If we have a system, if we're observing a set of variables which constitute the state of a system, and the change over time of those variables is taken as coming from the state and the parameters and nothing else, we call this specifically an autonomous dynamical system. So here the rate of change of the system, the dynamic, is a function of the state and the parameters only. That's the only kind of system we've met so far. A driven system contrasts with an autonomous system in that the changes that we observe in the system are a function of the state of the system, of the parameters, and some expression involving t. That ties it into the passage of time and allows anything to happen. What it means is that the evolution of this system in time is not based solely on the properties of the system itself, but it is subject to external influences. It's a very small difference in the math that's captured very nicely here, but it leads to considerations of independence and non-independence, which become very important when we go to consider, for example, joint movement, joint action, things that we achieved together, where we may want to partition our contribution to a joint achievement and say, you did this and I did that. But we may also want to show where the two systems become non-independent, as when, for example, we shake hands. Here's a little example from the scientific literature. So chick heart cells display their own periodic behavior. You can scrape them out of the heart, put them on a petri dish, and they will pulse. They have endogenous pacemakers, so they will beat boom, 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 all on their own. Their functioning within the intact heart is rather different, as there are several sources of several energetic sources, but on their own, each chick heart displays its own periodic behavior. It is, as it were, a law unto itself. We can understand the chick heart's beating through a model of the cell itself. And such a cell can also be influenced. So in the time recording on the bottom, you can see that a perturbation or a poke is given to the cell at one point, which briefly delays the endogenous activity of the cell, but shortly after the perturbation, the endogenous activity re-emerges. So the perturbation delays, modifies briefly the activity of the cell, But the endogenous autonomous activity of the cell reasserts itself. And you can see that in the continued beating thereafter. There's simply one slightly longer interval t there. In general, if a system is autonomous, it may of course be perturbed or influenced. And here we see the idealizations of this particular mathematical formalism. There is no such thing as a closed system. There is no system which is cut off from the world. But we may wish in science, we typically try to frame our observations so that we can understand something without all of its connections to the world. Having framed the system which now seems to us to display some sort of autonomy, it may of course be perturbed, but the manner in which it responds to that perturbation is governed by its own internal processes. So we saw the chick heart cell responding to a perturbation, but it was not controlled by the perturbation. The perturbation served to modify its own internal economy. This is in general true of living beings and is a very important characteristic of living beings. Autonomy is in many respects the signature property of what a living entity is. And in this respect, living entities can never be controlled. Their response to what you do to them comes from within, as it were, because living beings are self-generating beings. But they are not independent of everything, of course. And living beings enter into all kinds of relationships, coupling relationships, which is a theme we'll explore in the next video. But when we say that a system has autonomy, what we mean is that these relations that it enters into are, as it were, undoable, that there is some core to the system which is independent of its manifest relationships. This is, of course, an idealization, but it allows us to treat a living organism, for example, as a distinguished, self-generating, autonomous system. We'll look into relationships of coupling and entrainment in the next video.